Hello from Washington. My name is Nadia Vinogradova-Schiffer. I direct Ocean Physics program at NASA headquarters, Science Mission Directorate. I'm an ocean physicist and climate scientist, and I'm happy to spend the next 15 minutes with the COP audience talking about NASA climate science. Let's go. Next slide, please. So by the time you're hearing this message, COP26 is way under its way. But today, as I am recording my talk, not knowing the outcomes of the meeting, I am filled with anticipation and hope that we will choose the future that has a more habitable and comfortable climate that we rely on. And while world leaders do their job, we at NASA do ours. We literally keep our eyes on Earth using a large fleet of satellite missions, the observing system that our engineers design and build, and world-class scientists use to produce data, information, and knowledge of the Earth climate system. Let's explore two aspects of it today: Earth heat or energy and water. Next slide, please. One of the IPCC conclusions this year was this very tight, almost linear response of global temperatures to accumulated carbon emissions. The green line on your screens is what we've observed so far since 1850, the left side of the plot. And colored lines are projected scenarios of future climates until mid-century 2050, the right side of the plot. As the time goes on and more carbon is accumulated in the atmosphere, Earth temperatures are rising. Since 1850, more than 2,000 gigaton of anthropogenic CO2 was emitted, which raised our global temperature by more than 8 degrees Celsius. So why is it so? Let's break it down a little and check into physics behind it using NASA data. Next slide, please. We'll start with the energy source. Almost all of the Earth energy comes from the sun. Some of it gets reflected back to space by clouds, ice, and particles, but most of it is absorbed by the Earth's surface. That makes Earth warmer. To cool off, Earth releases energy back into space. So NASA satellites measure this outgoing energy, which has the form of thermal infrared radiation. And from this and the energy conservation principles, meaning that energy in equal to energy out, we can determine how much heat has been accumulated in the Earth over time. So how much is it? Let's see it on the next slide. Not all of the energy that is trying to escape from Earth gets back into space. Some of it gets trapped in the atmosphere by the greenhouse gases and then re-radiated back to Earth in the, as the greenhouse effects. See those red arrows on your left plot. If there is no greenhouses at all, our planet would have been very cold and uncomfortable, about -C on average. But obviously, this is not the case. And in fact, we're having too much of accumulated greenhouse gases in the atmosphere. Over the past 2,000 years, atmospheric concentration of CO2 doubled. See this red line on your plot on the right. Today, it is higher than at any time in at least 2 million years. So I think it's time to find a better way of doing business so we can reduce the amount of emission and stop trapping this unnecessary heat and let it go back into space where it came from. The last time the Earth was as warm as it is today was 100,000 years ago. So think about it. We built our lives, our infrastructure, our economies, our homes, everything around a different climate. Are we ready for a new climate state? And what is it, the new state of climate? Let's dig in on the next slide. So where is the global warming going? Well, most of it is going into the ocean, about 93-94%. So oceans are saving the day by absorbing and storing extra heat and delaying the full impact of global warming. Over decades, oceans accumulated an enormous amount of heat, a few hundreds of zettajoules. And for context, a zettajoule is 10 times larger than the global energy consumption of all human population today. So more heat stored in the ocean means that more heat will inevitably be released into the atmosphere. If it happened instantaneously, which is not the case, that would warm our low atmosphere by more than 30 degrees Celsius. This transfer, of course, is not physically possible. That's not how the system works, but rather the release is slow and gradual. But think about the huge ocean thermal load. An even small release of energy will lead to uncomfortable warming tendencies. How much more uncomfortable? Let's check on the next slide. So recall a few slides ago that every time we add another ton of carbon in the atmosphere, we raise global warming by about half a degree on average. And with every additional amount of warming, the change gets larger. So what futures are we choosing today? Here are the IPCC projection of surface temperature of 3 future climate scenarios when the world is warmer by 1.5 C, 2 Celsius, and 4 Celsius. Notice that regional changes can be even higher than this global average target. So the heat in your hometown can become unbearable, like life-threatening for humans, or unsustainable for our crops and agriculture, or breeding grounds for new diseases, and favorable condition for extreme weather events. Oceans, of course, will continue doing its parts by redistributing and absorbing this extra heat, energy, and moisture, but at what price? In other words, what happens with the oceans when the oceans are getting warmer? Well, you get even more oceans. Let's move to the next slide. The most direct and measurable impact of global warming are rising seas. Over the past 3 decades, NASA has been recording sea level rise both globally, you plot on the right, and regionally, this rotating globe on the left. And I remember giving sea level talks 5 years ago where this rotating globe had more colors in it, like Eastern Pacific Ocean was still blue or not a significant sea level rise was observed. Today, the colors are becoming more saturated towards yellow and red, meaning that almost all over the globe, the seas are higher today than they were 30 years ago. And some of those changes are here to stay. We've increased the volume of oceans for a very long time. And it seems that another half a meter of global mean sea level rise is inevitable. Well, whether it's more than that, again, it's up to us. And the consequences of rising seas are already felt today. It threatens our economy, infrastructure, ecosystem. Coastal oceans is where most of us live. So hundreds of millions of us are exposed to coastal hazards like floods and storm surges, coastal erosion, disruption of freshwater supplies, etc. So as we at NASA continue measuring, understanding, and predicting climate changes, including sea level rise, we want to provide this information in an accessible and useful way so the decision maker will make an informed, science-based choices. So how do we do it? Here's an example on the next slide. I'm on slide 9 and I hope you are too. And this is an example of NASA partnership with IPCC to deliver sea level projection across the globe. So users and planners can explore sea level rise under various climate that the humanity is going to pick and see for yourself how high would be the oceans in 10 years or 20 years or maybe next century. You can do it globally, or you can pick a favorite coastal city by clicking the button, and the closest one I found to Glasgow is on your screens. You would also see the physical processes behind those changes. Is it ocean thermodynamics, or melting glaciers, or ice sheets, land water storage, or vertical land motion? So remember, this information is there. It is free, it is accessible, it is current. Thousands of engineers and scientists worked on it to produce this knowledge, and now it's at your fingerprints. So make good use of it. Decision is yours. So for my next and last slides, I wanted to conclude that whatever decision is made during COP26 and implemented strategies later, NASA will continue doing its job, monitoring state of the Earth system. And by observing the changes in real time, NASA will be keeping watch of the effectiveness of these climate solutions and decisions that humanity makes. And while doing though, we're making hundreds of new discoveries. We are unveiling new physics, new connections, new phenomena that never been observed before. and explaining what's happening with the Earth as a system everywhere on the globe, now and in the future. So keep in touch, and thank you for joining NASA today. Until next time, goodbye.